Thank you, folks. Hi all, I'm Alex. I am an R&D engineer at Tenderly, and today I'll be talking about our approach to transaction threat analysis. My background, I come from data science and machine learning areas, and in general, before joining Tenderly, I didn't have much exposure to blockchain or blockchain security. But while I was working on it, I realized that a lot of concepts from data science can quite naturally be transferred to transaction security. So let's start. So why exactly am I saying transaction security? Because that's the level at which we do security analysis. So I don't know if you're familiar with this screenshot, if you ever used Tenderly Explorer. So this is just a part of the transaction which is unrolled. So you can see here there are multiple jumps inside a single contract. There are calls or different contracts, delegate calls. There are also storage persisting. So like you can see in a single transactions, you pretty much have a huge graph of just things happening all around. So that's why I wanted to emphasize that a transaction is a clearly rich, multidimensional source of information from which we can learn a lot what is happening on blockchain. Like I said, I come from data science background, and here I would like to mention the concepts which I found can easily be translated into blockchain security. So on the one side, on one side we have data, on the other side compute. Related to data, we have data quantity, so of course you need a lot of data to, well, create any insight out of it. Data quality, so the data you have should be quite accurate and in general should have a lot of context, more context the merrier. Data privacy, in general, like you still want to keep some private informations out of the way, so you cannot really create insight out of all information. And data relevance, so some data points can be relevant at some time, then later can be not that relevant, or they maybe only apply to some specific security problems, not to all of them. On the other side, we have compute. So here you can see, like, generally the four steps of the compute pipeline. We have data gathering, where raw data is gathered and stored. We have data preprocessing, where raw data is just enriched with additional context and metadata, so it's easier to be used later. We have model training and insight creating, where you create some insight from which we can later, in the inference step, predict some next actions or do some risk analysis. So let's go quickly one by one. Data quantity in blockchain. So good thing here, like, blockchain is huge. We have a lot of data there. And what's even better, that blockchain is kind of an immutable data set. So what happened once, that pretty much is persistent. It cannot be changed, so you can use it for good. For example, on Ethereum mainnet, we have more than 1 million transactions a day. Up until now, there have been more than 2 billion transactions. And like I said, each transaction is a graph of things happening. So that's really, really a lot of data. And nowadays, L2 solutions are trending. So like we have even like more transactions happening. Like on Base and Arbitrum, there are like 5 million transactions a day. On like the L2 solution PsyCompad, there are more than 10 million transactions a day. And not just that we're having a lot of transactions, there's also more and more new users, more new addresses being active each day. And not just that, they are active, they're also active in different blockchain ecosystems. So we have some users being active in DeFi, some in gaming, which is really good because we can not just learn a lot, but we can learn a lot in different subsections and probably be even better in solving specific problems of security on blockchain. Data quality. Okay, so I mentioned we have a lot of data, but a problem here is that that data is quite raw and low level. So it's not really usable at the basic stage you get it from different RPCs. That's why it's quite important to use domain expertise, like knowledge of protocol mechanics, of generally historic threat types, analysis of some older hacks, to enrich the data with some context, and the idea here is to reduce the noise, increase the signal clarity, and just all in all have better data, in a meaning that it's even in some cases human readable, so we can even sometimes analyze it by hand. This is pretty much the gist of my presentation today. I'll return back to it in the second part of the presentation with more detail. Data privacy, so this one is a bit interesting here because, so in general, transactions are implicitly transparent, so you can kind of see what is happening there. But the thing is that the user is not fully identified, but it has like pseudonymous address by which is identified. And if you really want to link it to some real world entities, which is not really done that often, you have to go through a bit more a bit longer process of analysis, and that's only done in some sensitive financial activity cases. So yeah, in general, you can say that there is an issue of balancing transparency and anonymity on blockchain regarding security. Data relevance. So one thing here, I said we have a lot of data, but the thing is, as networks are continuously evolving, so you have protocol upgrades all the time. And on top of that, like I said, L2 solutions are trending nowadays. So generally, user behavior is kind of changing. You cannot really use old data all the time. So you can always be kind of up to date and make sure that the data you're using is relevant to the current state of situations. And also one thing I previously mentioned, for some more specific security problems, like you can only use maybe DeFi data like swap and trade transactions if you just want to do DeFi risk analysis. Or for example, for NFT security, you should maybe only be checking transactions related to NFT marketplaces. Okay, so back to the other side, compute. Like I said, first stage, data gathering. So yeah, once again, like good thing we have an abundance of data, but a problem there is that you have to find a really efficient way to process it and store it. So it's really, really important that you kind of do it in parallel, much, much faster than in general how in real-time transactions are happening. So it's of utmost importance to have a high-quality, fast transaction trace source. If you haven't tried, check Tenderly. Next step, data pre-processing. So yeah, like I mentioned beforehand, the data you get from most of the sources is quite raw. You have to pre-process it. In best possible cases, you even get to some kind of human interpretable level. The idea here is to use the general expert knowledge. So this, like I said, I'll return back to this in the second part of my presentation. The training process, well, it's a bit interesting here. So yeah, I said we had a lot of data, but I never mentioned any labels. So in general, it's quite hard to find labeled data sets for blockchain, specifically for security issues. It's quite hard to find them, and you find them, they're generally not full. You always have something missing, and you have to spend a lot of resources just to maybe label it manually. So standard supervised learning here is quite impractical. One of the alternative strategies you may want to try here is to develop some heuristics to kind of auto-generate weak labels. We call them weak because you're not really 100% sure they are fully true, but you just create a lot of them and you hope that your training algorithm will just catch what the gist is there. Combine those with the small amounts of strongly labeled data you have, and you can probably bootstrap some original insight. With time, more data would come, and you could definitely maybe get to better performances. And in the end, inference. So this part of the compute pipeline is the only one which is visible to the end user. So here, the biggest issue is to make it extremely fast. We're talking here about like sub-second execution times. And why is that? Because In general, blockchain transactions have some latency by design. What you don't want to do is to make the user spend even more time waiting for transaction to be checked for some security risks. You want it to look like it's not even happening, and just give the user the green light, like your transaction is good to go, or your transaction is potentially risky. Okay, so like I said in the second part of the presentation, I'll focus more on the data pre-processing, where we increase the quality of the raw data we get at the beginning, by mentioning a couple of examples how you can just enrich address intelligence, whereby address intelligence, I mean the information you have about an address, either static or dynamic, meaning the one that is the insights you can learn by looking at the addresses activity on chain. The first one of my favorite examples, address similarity. So we know that addresses are like 40 characters long. You would say chances that there are similar addresses are quite low, but the similarity here, I define it a bit different. I just look at the first four and last four characters. And why is that? Is because in a lot of applications, like platforms where you just have your transaction listing and stuff, just for the sake of practicality of the user interface, only those characters are shown, and you have like 3 dots in between. So that's why an attack like address poisoning is quite possible, and in the latest analysis I did, it's quite often. It's happening like every like 10, 15 minutes, you can find an example of it. So on the right, you can see an example of it. Let's say we have the purple address, the Alex one, which is regularly transacting with the blue address 1234. So I'm regularly talking, that's an address I trust, and all is good. Then we have an attacker who generates a bunch of addresses, like it's not that expensive, they can generate a bunch of them, and then they can go through like latest blocks and just try to find one address which is active there and which is similar to any of their addresses. So in this case, we have the red address, which has the same first 4 and last 4 characters as the blue address. And the attacker can just send some small amount to me, or even like near $0 value amount, with a single goal, just to enter my contact list. And for example, if my contact list looks like this, I've only bolded the first 4 and the last 4 characters, because chances are like only those would be shown. I would have to like hover over it or just check it out. If I'm naive, if I'm not checking fully the stuff, I can just click on the attacker's address and transact with them and send them some assets. A similar thing can happen also with token symbols. You can easily find like thousands of copycats of USDT and USDC tokens. I just searched on CoinGecko. People are creating them all the time just because they want something like this happen. They want a user to accidentally just click on that token and maybe try to buy it or something like that. Next thing, token value trend. So imagine when you're just like buying a token or doing something with it. In general, on most applications, you only see like its current value. You don't see its trend, so you cannot see a situation like this, which you're probably familiar with. This example. It happened like 10, 15 days ago. But nevertheless, the thing here is this token is clearly unstable. This is an example of rug pull. A rug pull is an attack, which is where the token holders or creators just hold large amounts of that token. They just wait for its value to be built a lot, and then they just sell all of it, and the value plummets. So in cases when you know just the current value, you cannot really be sure what's happening with it. When you know the trend, you can maybe have much more insight into what you're doing. Like you can have a signal saying, okay, this is clearly an unstable token. Are you sure you want to trade with it? Gas usage. So this one is also interesting. On the left side, I'm mentioning user gas usage stats, which is pretty much like basic statistics about the gas usage a user has when it's sending transactions. So here I just picked a random EOA, which has a huge sample size. So like they have like more than more than 255,000 transactions in their history. But you can see that like the mean gas usage is near 21K, meaning they're mostly like doing just simple ETH transfers. But for this particular address, I found an example where they are just, maybe they wanted to do it, maybe they didn't, but they spent a lot of gas. So in general, this is a case where you would feel that the user would want to have a signal like, okay, in general, you're spending much less gas. Are you sure you want to submit this transaction because it's going to be much more expensive than you're used to? On the other side, we're collecting the same statistics about gas usage, but for each method of each contract. So here, I have an example of Gempad. I'm not really familiar with the contract, but there was an attack on it a month ago. So its collect fees function in general has gas usage with this mean around 8.5 million. But a month ago, somebody found an issue with it, and they did a re-entrancy attack on it. And that transaction spent 3 times more gas than its average. So, like, if the owner of the contract had some kind of signaling, like about their statistics with gas usage, they could have immediately known that something is happening with their contract. On the other side, the contract itself might be malicious sometimes. They might change their own implementation through some proxy, but that can also be realized by perhaps seeing the decrease, like a huge decrease in their gas usage. Historical context, one more quite important thing. So in general, this is some of the cases you want to be really aware of. So whenever you're first time interacting with someone, you want to have some kind of a signal, okay, this is an unknown address to you. Are you sure you want to transact with them? Or also, there are different types of transactions. So if there is an address which is constantly sending me some assets, but maybe it's totally random to me, I want to be aware when it's the first time I am sending assets to them or just approving them to spend my assets. On the right side, you can see a bit more interesting case. So there's no direct contact, but for example, let's say the node on the bottom is a Tornado Cash address. Tornado Cash, for those of you who don't know, it's just a mixing service where people just push their assets anonymously and then withdraw them at some point using some confirmation codes. It's used a lot for money laundering, so you don't want to be connected to them either directly or indirectly. And this is a quite regular pattern where a malicious address, the X one, the red one, has a bunch of proxy addresses through which they contact the Tornado Cash. So they deposit, they withdraw cash there. So they are doing some stuff which are not really supposed to be done. And even though like it's not direct contact, you still want to be aware that of this pattern, and you, the yellow, the naive node, don't want to have any contact with the red node. And the last thing I want to mention, probably my favorite one, is analyzing function execution flows and creating a correlation with, of the function execution with the well-known events like transfers, approvals, burns, meets, and stuff. So this way, by not doing the static analysis of a function, but by doing like dynamic analysis of its execution, you can build a behavioral profile of the function. And that way, you can say, okay, so on the right side, I have an example. We have Tether, super well-known contract. It has the function transfer from, and as expected, that function in like 99.97% successfully transfers assets from one of its parameters to another. And that's supposed to be happen, and that's kind of, you can be sure that the function for which you can even see the code is doing what it's supposed to be. But below, I found some random unverified contract, and I found some of its function, which also has super hard correlation with a mint event. So even though you cannot see its code, you can kind of know what that function is doing. So whenever a new user maybe wants to call it, that you can just say, okay, I'm not really 100% sure, but probably this is what's going to happen. So to sum up, by leveraging like expert-driven knowledge for data pre-processing, we can transform raw blockchain data, which is fully accessible, to actionable intelligence, improving threat detection and model training, and making real-time inference faster. Thank you. That's all that I prepared for today. If you have any questions, feel free to ask.
Thank you, Aleksandar. Questions from the room?
Yep. Hiya. You mentioned needing quick access to trace data and then proposed using Tenderly. I already use Tenderly. Just out of interest, how does Tenderly get the trace data quickly at the head of the chain?
Ooh, yeah. Not really my area of expertise, but so in general, especially for this case, we did a lot of specific optimizations. So most of them are around just having like the latest blocks like in some cache and really be much faster to be accessed. But also we made sure that there's enough time for us to analyze them before processing to the next batch, because it's quite important to still have that chronological order of stuff. So you want to know, okay, this is what we learned here, but that happened before the next thing we learned. So yeah, we did a lot of optimizations in both, parallelizations for both parallelization and for both that temporal ordering of stuff.
Okay. So is there just a lot of hardware as well? You've just attacking the problem
it was
at
part
scale.
of it, definitely. Yeah.
Any more questions? Yep.
So thank you for your talk. I have a question for you. Since you are doing your PhD in graph neural networks, any work in there?
Sorry?
Any work in graph neural networks?
Well, yeah. I mean, so in general, I just started my research, so it's mostly about like raw graphs with not much context to them. Generally, the data sets I prefer are transactional data sets. Currently, I'm working mostly with like classical transactions, like old banking systems. But yeah, I do plan to move a bit more to Web3. I would say like there's definitely a future there, but in general, I didn't see much successful research just because there's a lot of data in Web3. Like I said, like each transaction is a graph for itself, and then you have like the graph of all addresses, contracts, and stuff. It's just like a very multidimensional problem, which I think is going to take some time to be solved.